Hi everyone, and thanks for checking out this video on approximate pattern matching. My name is Philip Wellnitz and this is joint work with Panagiotis, Charalampopoulos and Tomasz Kociumaka. Let us recall the pattern matching problem. Here we are given a text T and a pattern P in order to find all occurrences of P in T. For instance, there is exactly one occurrence of cake in pancake. Most of the time, searching for exact occurrences of the pattern is not good enough though. Think of spelling mistakes in the text or the pattern, or just noisy data in general. Hence, in this video, we consider approximate pattern matching, where each occurrence is allowed to be slightly different from the actual pattern. First, we consider the pattern matching with mismatches problem. Here, we search for substrings of T that are at Hamming distance at most k from the pattern. That is, we allow for up to k mismatches when searching for occurrences of the pattern. For instance, if we allow for up to 2 mismatches, we can find unpan in pancake. Naturally, we're not the first ones to study this problem, so let me quickly highlight some of the flagship results. After a long line of research, Clifford et al. Gave an algorithm solving this problem in time linear in the length of the pattern text, roughly quadratic in the number of mismatches allowed. In 2018, Gaudykovsky and Uznansky gave an algorithm improving upon this for some choice of n, m, and k. They also proved that their algorithm is essentially optimal by designing a matching conditional lower bound. Hence, you could say that pattern matching with mismatches is essentially fully understood. However, allowing for only mismatches is rather restrictive. For instance, it doesn't cover the common case of surplus characters. Hence, we also consider the pattern matching with errors problem. Here, we search for substrings of T that are at added distance at most k from the pattern. Recall that the added distance between two strings is the minimum number of insertions, deletions, or modifications of characters required to change one string into the other string. Coming back to our example, we allow for up to 2 errors, we can also find plunk in pancake. Again, we are not the first ones to consider this problem, so let me highlight some of the flagship results for this problem. Again, after a long line of research, Cole and Haruran gave an algorithm solving this problem in time linear in the length of the text in the pattern, roughly biquadratic in k. From the lower bound perspective, however, the highly celebrated result by Bakers and Indig for computing the added distance of 2 strings only rules out algorithms faster than roughly k squared. I'm sorry to disappoint you, but we still don't know how to shrink this gap. Instead, we consider the case when both the text and the pattern are huge. Think of the human genome or large bodies of natural text. A natural approach in this situation is to compress the text and the pattern. In particular, we want to solve the approximate pattern matching problem without decompressing the compressed data first, so that we actually gain some speed up over the known algorithms. A mathematically elegant way to capture a plethora of known and different compression schemes, such as Lample-Ziff compressions, are so-called grammar compressions. For a string T, a grammar compression of T suggests a context-free grammar that generates only T. We may also assume that such a grammar is a straight-line program, or SLP for short. A straight-line program is a set of non-terminals and productions. Each production takes a non-terminal and produces either a terminal symbol or 2 non-terminals that have appeared beforehand. The starting symbol is Tn. As an example, take a look at these 3 productions. Currently, they are not all that useful, so let us add some more productions. As you can see, with these 5 productions, we can produce the string A and P. However, this SLP doesn't compress A and P yet, so let us add some more productions. Getting better, and now with 7 rules, we produce the string unpan of length 8, so we do compress that string, albeit not by much. However, it is easy to see that in the best case, such an SLP may give up to an exponential compression. Again, we are not the first ones to study pattern matching of grammar compressed strings. Here are some flagship results. For the exact pattern matching case, a breakthrough result by Yes showed that there is hope for algorithms that don't first decompress the SLPs. He presented an algorithm running in time roughly linear in the compressed sizes. Note that in this case, the O tilde notation also hides some logarithmic factors in the uncompressed lengths of the strings. For pattern matching with mismatches, I want to highlight a recent result where co-authors and I obtained an algorithm that worked for compressed texts but uncompressed patterns, which is still the best we could do up until now. For pattern matching with errors, the situation is even worse. The best algorithm so far ran in time quadratic in the compressed sizes with some extra dependency on k. Finally, in this work, we managed to improve upon both of these running times and give the first algorithms that run in roughly linear time in the compressed sizes of t and p. Even more, our approach also yields alternative algorithms for the uncompressed setting, which are not slower than some of the fastest known algorithms for that setting. We obtained these results via improved and new structural insights into the solution structure of approximate pattern matching problems. What do I mean by structural insight? In a previous work, co-authors and I showed the following theorem. Given a pattern P and a text T that is not much longer than P and a threshold K, at least one of the following is true. 1. There are only very few K mismatch occurrences of P in T. Or 2. P is almost periodic, which here means that P is at Hamming distance at most 6K to some string with a small period. Also, we proved some additional insights for the almost periodic case. Now in this work, we improved this insight as follows. First, we further reduced the bound on the number of occurrences, and second, we decreased the number of mismatches required for the almost periodic case. Of course, you may now ask, are these bounds finally optimal? And I have good news for you. First, consider the non-periodic case. Take a look at this example. Both T and P consist of a long part of A's followed by a long part of C's. So both T and P are far from periodic. Further, there's exactly one exact match of P and T, but if we allow for up to K mismatches, we can also shift P for up to K positions in either direction, resulting in 2K plus 1 K mismatch occurrences of P in T. So, even a non-periodic pattern may have order of K mismatch occurrences in a text. Second, consider the almost periodic case. Take a look at this example. Start with the all A string for both T and P, and change in total K random positions in T and P to a C. So both T and P are with high probability, again not periodic. Further, when allowing for K mismatches, P occurs at every position in T. Note that this only yields a requirement to allow for up to 1 plus epsilon k mismatches in the almost periodic case. However, in theory, our proofs could be easily reworked to yield also just that 1 plus epsilon bound. Now, this was the structural insight for pattern matching with mismatches. What about pattern matching with error? Here, we obtain a similar result. The only difference is that the bound in the non-periodic case becomes quadratic again. Now you may think that this is not optimal. But in fact, we proved the even stronger result that all k error occurrences must lie in order of k intervals of size order of k each. And now there is an example showing that this result is tight as well. I will skip this example here though. In general, in this video I will focus on the Hamming distance case. Our proofs generalize to the edit distance case though. Note that this is yet another nice aspect of our new technique. The old approach did not allow such a generalization. So, let me give you some more detailed insight on how we prove our results. As our key lemma, we proved that any string p satisfies at least one of the following. 1. P contains 2k disjoint breaks, where a break is a rather long part of P that is not periodic. Or 2. P contains disjoint repetitive regions that span a constant fraction of P, where each repetitive region locally looks like the almost periodic case, but with a guaranteed minimum number of mismatches to the corresponding periodic string. Or 3. P is almost periodic. Let me quickly demonstrate why this key lemma is all we need. First, if we are in the almost periodic case, we are almost good already. Note that we just need to reduce the number of mismatches to the periodic string. To that end, we use this observation. If P has already 2k mismatches to some periodic string with a period of m by k, then there are at most order of k mismatch occurrences of P in any text T. This then yields either the first or the second case of the main structural result, depending on whether P has at least 2k mismatches to some periodic string. Now, for the repetitive regions, recall that I mentioned that they locally look like the almost periodic case, that we additionally have a guaranteed minimum number of mismatches to the corresponding periodic string. What this means is that we can essentially use the aforementioned fact from the almost periodic case again. But this time, this observation always yields the desired bound to the number of k mismatch occurrences of P in any string T. Finally, for the breaks, we can do something similar to the almost periodic case. To be precise, we use this observation, that if there are at least 2k disjoint breaks, then we cannot have more than order of k mismatch occurrences of P in any string T. In total, this shows that proving our key lemma really is all we need to do. So, how do we prove our key lemma? Take a string P. We then construct either 2k long breaks or long repetitive regions. Or if we fail, we know that P is almost periodic. To that end, we process P from left to right, m by 8k new characters at a time. If such a fragment has a large period, we just found a new break and add this break to the set of breaks. Otherwise, such a fragment of unprocessed characters has a small period. We then take the shortest prefix of the unprocessed part of P longer than m by 8k, that is a repetitive region, and add this repetitive region to the set of repetitive regions. If at some point we found the 2kth break, we are done and return the set of breaks. If the repetitive regions found so far cover a constant fraction of p, we are also done and return the set of repetitive regions. However, if by searching for a repetitive region we reach the end of p, we need to do some extra work. Namely, we discard all breaks in repetitive regions found so far and search for a single repetitive region starting from the end of the string. If we succeed, we can be sure that this repetitive region covers the constant fraction of p, so we can return it. If we fail to obtain a repetitive region again, we now know that P is almost periodic. This completes the rough overview of the ideas required to prove our key lemma and by extension the structural insight. In the rest of this video, let me focus on how we turn these structural insights into faster algorithms. In the first step, we observed that we can implement our key lemma and dimension observations using only a small set of essential operations, and all of them are rather common tools when working with string-like objects. As these operations are so essential, we coined the corresponding model of computation the pillar model. Now, how is this pillar model useful? We use the pillar model as follows. First, we give fast algorithms using only the pillar model operations. Second, by combining existing tools, we obtain fast implementations for the pillar model in 3 different settings. Note that these implementations themselves are much easier compared to writing down our algorithms for each setting separately. Note further that once you implement the pillar model operations in your setting of choice, you get fast approximate pattern matching algorithms essentially for free. So let me give you the theorem statements. Don't worry about the details and just focus on the running times. For pattern matching with mismatches, we obtained an algorithm using roughly k-squared pillar operations. Note that in this case we lose the log k factor of assorting k-squared integers. Similarly, for pattern matching with errors, we obtained an algorithm using roughly k to the 4th pillar operations. Now, we just need to combine these algorithms with fast pillar implementations to get fast algorithms for different settings. As a toy example, let me mention the uncompressed setting. Here, implementing the pillar model is rather easy. Everything apart from the internal pattern matching operation could be an exercise in an algorithms and data structure course. In total, we then obtain algorithms that are not slower than some of the fastest known algorithms for this setting. Next, the fully compressed setting, where both t and p are given as a straight line program. Here, we can use Yesh's celebrated recompression technique to implement all pillar operations in time log cubed in the length of the uncompressed strings. This then yields the results I advertised earlier, the first near linear time algorithms for the fully compressed setting. Note that even for a case when only the text is compressed, these algorithms are faster than the fastest known algorithms. Finally, let me quickly mention the third setting we considered, namely the dynamic setting. Here, we want to maintain a data structure that supports creating new strings, as well as splitting and merging existing strings. We want to extend this data structure with queries that allow us to compute approximate occurrences of any of the strings in any other of the strings. Using optimal dynamic strings, we can implement each pillar operation in log² time. And this then gives the following results. Note that our data structure is faster than recomputing the solutions from scratch after each update. So we actually save something new. To summarize, in this video I gave you an overview on how to obtain the first almost linear time algorithms for fully compressed approximate pattern matching by demonstrating a unified approach. And this brings me to the end of this video. Thank you for watching until the end, and in case you are interested, the full version is available on arXiv.